All right, in the last portion of today's lecture, we'll go through a few practical implementation details for neural networks. So here's our neural network that we saw in the previous section, and there are a few things that we need to figure out before we can actually train it with backpropagation and gradient descent. How many layers should the network have? How big are these layers? What type of activation function should we use? In regard to activation functions, one choice that we learned about in the first part of the lecture is the sigmoid. And we talked about how the sigmoid is kind of what you get if you imagine that each feature is sort of a binary logistic regression problem. But you don't have to use the sigmoid. You can actually use many other activation functions. And one particularly popular choice is something called the rectified linear unit, or ReLU. The rectified linear unit takes the previous activation, let's say Z1, and it sets A1 to be the max between 0 and the corresponding entry of Z1. So whereas the sigmoid looks like this curvy thing that I have in the middle of the slide, the ReLU looks like this. It just has a positive branch that is kind of fully linear, and then it has a negative branch that is flat. This might at first seem like a peculiar activation function, right? It's like half of a linear function. It kind of seems like maybe it's insufficiently nonlinear. But actually it ends up working really well. It has a number of very appealing properties. One really appealing property is that it is computationally extremely cheap to implement, which means that for very large neural networks, it can actually speed them up considerably. The other nice thing about the ReLU is that its derivatives are really, really simple, and that also makes them computationally efficient and also easier to work with. So in practice these days, actually, the ReLU is by far the most popular activation function, although sigmoids and things like tanh functions are also sometimes used. All right, another detail that we have to talk about for actually implementing neural networks is the bias term. So this is the linear layer as I described it before. And this linear layer has a major limitation. Let's imagine that AI is just a vector of zeros. In this case, the linear layer can never produce any output that is not zero, which means that you will always have zeros everywhere, which means that if the input to the network X is itself a vector of all zeros, you'll only reproduce zeros, which means that this kind of neural network can never represent certain functions. It's not a universal function approximator. A solution to this is to add what's called a bias vector. This is completely unrelated to the bias variance thing. It's just called the same thing, but completely unrelated concept. And that turns linear layers into this. It says that Zi plus 1 is equal to Wi AI plus a constant vector Bi. This is also sometimes called an affine layer. It turns out that if you have a neural network that has these kinds of layers and a nonlinearity like a sigmoid, if these layers are big enough, you can provably approximate any function to an arbitrary level of precision. You cannot do that if you don't have these biases. So now the parameters of your neural net will consist of the weight matrices W1 and W2 and the bias vectors B1 and B2. And this is very standard. Almost always if you have a linear layer, you will have these biases. All right, now so far we're almost done fully specifying everything we need for our neural networks. What else do we need to actually implement backpropagation? Well, we need to be able to compute df d theta f and df dxf for every function. So for every function we have in our network, these two quantities need to be computable. We don't even need to construct the Jacobians, we just need to implement a function that multiplies delta on the left by the Jacobian. Once we do this for every type of function in our neural net, then we'll be done. So we need to do this for linear layers, for the softmax plus cross entropy, for sigmoids, for ReLUs, and so on. Most of these are pretty easy, but I will go through some of them in this lecture just to work them out, and hopefully for the remaining ones you can figure them out on your own. Probably the most complicated one is actually the linear layer. It's also the only one that has parameters, which is part of what makes it so complicated. So the linear layer is given by this expression, so Zi plus 1 is equal to Wi times Ai plus Bi. Or, just for notational convenience, I'll actually drop the superscripts and I'll write it as Z equals Wa plus B, just to keep things concise. Now, really quick, what is XF? XF is the input to this function, so XF is A. What is theta f? The parameters. Well, the parameters are W and B. If you actually want to turn them into a vector, you would stack up all the columns of W into one giant column and then append B at the bottom, and that gives you a giant vector called theta f. So what we really need is we need the derivative with respect to W, the derivative with respect to B, and the derivative with respect to A. We need all of them. All right, so I'll simplify notation, drop the superscripts, and theta f refers to W and B, and xf refers to A. So let's start with the first derivative we'll work out, which is actually the hardest one, dz dw times delta. Part of what makes this hard is that W is actually a matrix. But if you remember what we talked about when we discussed multivariate chain rule, when in doubt, when something is uncertain, just write everything out using scalars. So the ith dimension of z, zi, is equal to the sum over k over all entries in A of wik times ak plus bi, right? I've just written out explicitly what this matrix vector multiplication expression for the linear layer actually represents, right? So now everything here is a scalar. Zi is a scalar, wik is a scalar, ak is a scalar, etc. Now, dz dw times delta can be obtained as a sum over every entry in delta of dzi dw times delta I. This is not an obvious statement. And in fact, there's something a little bit complex here because dz dw is the derivative of a vector with respect to a matrix, which means it must actually be a three-dimensional quantity. So you can think of it as a cube where every slice of that cube is a matrix of the same dimensionality as W, and the number of slices is the number of dimensions in Z. So for every dimension in Z, there's a different W-shaped derivative. Now delta has the same dimensionality as Z. So if we want to multiply delta by this cube, the way that we do it is we actually end up multiplying each slice by the corresponding entry in delta. So you can kind of think of it as taking this long, thin thing delta and then stretching it out so it's cube-shaped, repeating every entry, and then just pointwise multiplying them, squishing them, and summing them together. And that's what the expression here is showing. And that will give you a matrix of the same dimensionality as W, because you're basically summing over all of the slices of this cube. So we need to calculate dzi dwjk. That'll give us the numerical value of every entry in this cube. And we can do this just by looking at the scalar valued expression, right? It's actually very straightforward using single variable calculus. If we just look at this expression, we'll see that zi only depends on wik. Now it depends on wik for every value of k, but only for the same value of I. So that means that if we want dzi dwjk, we know that that's going to be 0 for any j that is not the same as I, because any wjk does not influence zi if j is not equal to I. Or put another way, only those rows of W that have the same index as the index of I actually influence that entry in Z. If the rows match, then dzi dwik, which is the same as jk, is just ak, because that's the thing that multiplies wik in the expression in the bottom left. So visually, we could imagine, let's say, the derivative of the third entry in Z with respect to W would be a matrix with zeros everywhere except for the third row, and that third row would just be the transpose of A. So we just stick A into the third row and keep everything else as zeros. So that's what dzi dw looks like, and then it gets multiplied by delta I. Right? So in this case, if I is 3, then this dz3 dw would just get multiplied by delta 3. So every dzi dw actually has a non-zero row in a different place. So if we want to take the sum of those, we just stack all those rows together. So the full sum just consists of a matrix where every row is A transpose multiplied by a different element in delta. And if you're kind of familiar with linear algebra, just from looking at this, you might notice that this is exactly the outer product between delta and A. So you can actually also write this more compactly as delta A transpose. So that's really convenient, right? Because we have this scary three-dimensional thing, but we actually turn into an expression that we can compute with regular linear algebra that we're pretty familiar with. It's just delta A transpose. Okay, that was kind of the hard part. The rest is much easier. Let's look at dzdb times delta. Again, we'll write out the expression for z just to avoid going crazy with multivariate calculus. And here, it's actually pretty easy. We can see that dzi dbj is 0 if j is not equal to I, because only bi influences zi. And if they are equal, then it's just 1. So that means that you can write dzi dbj as an indicator for I equals j, meaning it's 1 if I equals j and 0 otherwise. And that means that the matrix dzdb is just the identity matrix. It's a diagonal matrix with 1s on the diagonal. And that means that dzb times delta is just equal to delta. Very, very simple. All right, last one, dzda delta, right? So that's the derivative with respect to the input. Again, we write out our expression for z. And from here, we can see that dzi dak is just wik, right? Because it's a linear function, very straightforward. Now remember that with our convention, the first index of the matrix is the denominator, and the second index is actually the numerator. So dzda is not actually w, it's actually w transpose because the indices are in the wrong order, right? So if you have some dy dx and you want the ijth entry, that's dyj dxi. So that means that if you have our Jacobian and we want the entry ki, that would be dzi dak, which would be wik. So this means that dzda is actually w transpose. And that means that what we want is w transpose delta. And you can check that this is true because you know that delta will have the same dimensionality as the output of the function, whereas w will have a number of columns equal to the input. So you have to transpose it if you want to have a valid matrix vector multiplication. So you need w transpose delta. Okay, and now we're basically done. We have the expression for dzda times delta, dzdw times delta, and dzdb times delta. This first one is just basically df dxf, and these second two together form df d theta f. So we've figured out how to do backpropagation with these linear layers. The rest are much easier. The sigmoid. So for the sigmoid, the input xf is this z1, the output is a1. You can write the sigmoid like this, 1 over 1 plus exponential of negative zi, so that's the ith entry of the output. The sigmoid is a per element operation, which means that the Jacobian df dxf is just diagonal, right? So there are no off-diagonal entries because each coordinate in the output is only affected by the corresponding coordinate in the input. So all you have to do is figure out the single variable derivatives and just plug them into the diagonal of this matrix. So let's work that out. The derivative, we can just work it out through the regular rules of calculus. It's we have like 1 over something, so you know that the derivative of 1 over something is the negative of 1 over that squared. And then you have an exponential, and the derivative of that is just that quantity. There's actually a typo here. The negative sign shouldn't be there. The negative sign up front. So you know that this 1 over x squared, you can write it as 1 over x times 1 over x. And the second part is just exactly the same sigmoid that went in. The first part, you can write out as 1 plus exponential of negative z over 1 plus exponential of negative z minus 1 over 1 plus exponential of negative z, right? Because the denominators are the same, and when you have the numerator, the 1 cancels off, and you're left with the same expression as the first term. And this now you can recognize as 1 minus sigma z. So that means that the full derivative is given by, and again I apologize, there's a typo, the negative sign shouldn't be there. The derivative is given by 1 minus sigma times sigma. Okay, so that means that if you want to multiply it by delta and get the ith entry of that derivative, again, the minus sign is a typo, it's 1 minus sigma zi times delta I. Very, very simple. And there are no parameters, so there's no df d theta f because there's no theta f. ReLU, the ReLU is even easier. So the expression for the ReLU is a max of 0 comma zi, and that means that the derivative with respect to zi is just 0 if zi is negative and 1 if it's positive. So it's just an indicator for zi greater than or equal to 0. Very, very simple. All right, so just to summarize, the backpropagation algorithm is an algorithm that starts at the last layer, and for every layer f, with inputs xf and parameters theta f, it computes dl d theta f by multiplying df d theta f by delta, and it computes a new delta, the derivative of L with respect to its inputs, by multiplying df dxf by delta. That means that for every function, you need to compute these two Jacobians, or at least the product of those Jacobians with delta. I went through it for linear layers, sigmoids, and ReLUs. The softmax plus Gauss entropy you can work out at home. It's decently straightforward, just a little tedious with a bunch of kind of standard calculus rules.